Hello. First, I'd like to warmly welcome you to the Anna Freud Center, to our second series of transformation seminars. Today is the third seminar of the series. We are really delighted that so many of you are able to join us. These debates are about your questions, about your thoughts, about us collectively developing a new vision for mental health. We look forward to receiving your comments and questions and hope that you all will be inspired to continue these discussions after the seminar. We are holding these seminars because we feel there is an urgent need for a national discussion around mental health of children, young people, and their families. Mental health has become a focus during the pandemic, and we hope that once we are beyond the crisis, we will be able to rebuild better for all of us, also in terms of the mental health of our young people who are at the sharpest end of their current pressures. The theme of the transformation seminars is thinking differently about mental health. We invite speakers to respond to a simple question, then ask them, what is their idea to transform children's and families' mental health in the UK? The seminars explore areas beyond clinical interventions, important though these are, to ask about how we can think about, do things differently, individually, collectively, and as a society to reduce the growing needs we have as individuals in our complex and interconnected social world, and tackle some of the underlying causes of mental ill health. After the presentation, we would like to invite you to ask questions. You'll see at the bottom of the screen that there is a space for Q&As. And if you'd like to submit your questions, we'll try to get through as many of them as we can in the time that we have available. Finally, if you are tweeting, please tag us at AFNCCF and use the hashtag Transformation Seminars. Today, I am honored and delighted to welcome someone who is a world-renowned, exceptional thinker in his field. When I say his field, it truly is his, because no one has the breadth and depth of understanding of the human mind quite like Karl Friston. Karl is a theoretical neuroscientist and a world authority on brain imaging and computational neuroscience. He's one of the most innovative thinkers about mental health alive today. He's Wellcome Professor of Imaging Neuroscience at UCL. He started off in psychiatry, but has been an independent and extraordinarily creative thinker, plying his own original furrow. His revolutionary impact on studies of the brain derives from his inventive use of probability theory to analyze neural imaging data. He invented a technique, statistical parametric mapping, or SPM, that is now widely used, almost universally, to look for correspondences in brain activity as measured by magnetic resonance imaging and cognitive function. He also invented voxel-based morphometry, a sensitive method for measuring the volume of brain structures. One classical well-known application demonstrated the increased volume of a region underlying spatial memory and the brains of London taxi drivers. Karl's dynamic causal modeling is used to estimate how different cortical regions of the brain influence one another. His current thinking about brain function is revolutionizing our ideas about perception, consciousness, mental disorder, and the nature of experience itself. The active inference framework, or prediction error minimization, is a relatively recent theory in mathematical neuroscience pioneered by Karl and his collaborators. It holds considerable promise to be the unifying theory of the brain. It is used increasingly to support theoretical predictions in experimental research, as well as advance the existing theory of perception and action. My deep admiration for Karl reached new heights through reading his contributions to Independent SAGE, or Scientific Advisory Group for Emergencies, a group of scientists who are working together to provide independent scientific advice to the UK government and the public, and how to minimize deaths and support Britain's recovery from the COVID-19 crisis. Karl's awards and honors are far too numerous to mention. I will just pick up a couple. He's a Fellow of the Royal Society, a Fellow of the Royal Society of Biology. In 2003, he received a Golden Brain Award, an international science award in the field of neuroscience given to people who made breakthroughs in research on vision and the brain. In 2013, he was awarded the International Weldon Memorial Prize, which is bestowed on the person deemed to have published the most noteworthy contribution to the development of mathematical or statistical methods applied to problems in biology in the previous decade. In 2016, he received the Charles Branch Award for unparalleled breakthroughs in brain research, and the Glass Brain Award for his lifetime achievement in the field of human brain mapping. This evening, we will hear Karl discuss the emergence of selfhood and how our sense of ourselves emerges in interaction with the minds around us, in a seminar intriguingly entitled Me and My Markov Blanket. We are very, very privileged to welcome one of the greatest thinkers in neuroscience today. Welcome, Karl.
Thank you very much for that lovely introduction. It's a true honor and pleasure, to be with you this evening. I am going to take the challenge of thinking differently about mental health very literally, to the extent that I feel I should apologize for how different this lecture might be from the kind of lecture that you would anticipate in this series. I'm going to attempt to provide a first principle account of dyadic interactions, speaking to selfhood as an emergent property of those interactions. But I'm going to do so from the point of view of a physicist. So I'm going to present a lecture of two halves. The first, again, I apologize, is really a foundational course in the way things work, the physics of self-organization. And I'm going to lift from that an understanding of sentience as an emergent property of self-organization. So I'm going to talk basically about the maths of the mechanics of mind. And I'm going to illustrate some of the simpler principles that emerge from this treatment using simulations of a primordial soup. And the end point really is a synchronization between what's on the inside and what's on the outside of anything that exists or self-organizes itself to a state of existence. Then I'm going to tell exactly the same story, but using the words and the language of a clinician or a neuroscientist, focusing on predictive processing and predictive coding formulations of how our brains work. But the endpoint is exactly the same. It's the demonstration that the things that matter in terms of our engagement with the world out there behind our sensorium rests upon a degree of synchronization that at the end I'm going to offer as a metaphor for alignment and the thing that glues together you and me in any dyadic interaction. So that's the roadmap over the next few minutes. I normally start the physics part of this talk with the question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, clearly, we're not going to be able to answer that question, but what we can do is just focus on the notion of a boundary of a living organism. And of course, to define anything, and specifically a living organism, you have to define what separates the organism from not the organism, me from everything else, me from other. And Schrödinger would be the first person to acknowledge that this boundary is in and of itself a statistical process. And I'm going to read that boundary by borrowing from Bayesian mechanics, the notion of a Markov blanket. So a Markov blanket, for those of you who don't know, is a very simple concept. It's a statistical set of states that insulates or separates internal states from external states on the outside. So graphically, we can consider some little universe here where each of these circles corresponds to some state of this universe, and the arrows or edges denote an influence of this state on that state. And what I can do is I can identify a set of states here encoded by blue as internal states, and then I can define the Markov blanket or the blanket states in terms of the parents, the children, and the parents of the children. So that affords a set of states that in effect provide all the information I need about the universe beyond those states that will enable me to predict what will happen on the inside. So in other words, statistically speaking, whatever is happening here is independent of what's happening here, because given or conditioned upon these blanket states. These blanket states hold all the information that I need to tell me about how I am going to evolve, about my dynamics. I'm going to make a further move here. I'm just going to split, bipartition these blanket states mathematically into two sets. One set, which we're going to call sensory states that influence but are not influenced by the internal states, and another set, active states, that are influenced by internal states but are not influenced by external states. And with that partition in place, I can now define the states of any particle or person, a priest, anything that exists as the internal states of that particle and their blanket states that comprise the sensory and the active states. And you may be asking, well, why have I done that? I think the intuition is more readily available if you think about some of your favorite systems. So one of my favorite systems is the brain. And one can consider the internal states of the brain as every state of synaptic activity, efficacy, connectivity that constitutes a particular internal state of the brain. And these internal states and your activity are communicated or influence active states, my actuators, my autonomic nervous system that produces changes in the external states out there, the physiological states of my body or the motor states of my motor plant that change the sensations, the sensory states that are picked up and impinge upon my internal states, so that I have this sort of circular causality where the internal states exchange with the external states through the Markov blanket, a dual carriageway where the influence of the inside on the outside is mediated by the active states, and the influence of the outside on the inside is mediated by the sensory states. And these arrows are what license my attribution of states to internal or external sensory or active, in the sense that they denote the conditional independencies that we've just described that define the Markov blanket. But this structure can be found anywhere that you can separate something from the rest of the universe. So, for example, a little cell will have internal states will correspond to the intracellular states. The active states could be the actin filaments that support the surface states, that push the surface states into the external milieu, the external states that reciprocate by changing the cell surface sensory receptors that cause changes in the internal states. And so this perception action cycle at this very elemental level is still in play and rests upon this Markovian partition into internal, external, and intervening blanket states. So what I want you to do now is to bear that in mind, but forget about it for the moment. What we're going to do next is just consider the physics of systems that self-organize. And then what we're going to do is to put the Markov blanket back in play and see what implications it has for the relationship between what's on the inside and what's on the outside. So this is a bit heavy. Again, I apologize for the mathematics. You don't need to understand the functional form of these equations, but I think they are useful just to sketch the architecture of the ideas. And in fact, if you are mathematically minded, their simplicity. So what I've done here is just drawn the kind of universe that I'm interested in. And I'm interested in universes that exist, that persist over time. So mathematically, that means that they have an attracting set. Another word for that is that they constitute a random dynamical system with a global random attractor. So more intuitively, I've just sketched out two states here. They could be the temperature of my body, say the concentration of oxygen, if I was a physiologist. And I've traced out over time the way that these states might change. This could stand in for anything. It could be very fast fluctuations in electrical and chemical constituents of a part of my brain that unfold over milliseconds to give me synchronized activity in the brain. It could be my heartbeat, two aspects of my heart contracting every second or so. It could be me getting up in the morning, having a cup of coffee, doing my emails, looking forward to lunch. It could be Christmas, Easter, summer holidays, birthday. This structure has to exist at any scale, at any spatial and temporal scale, crucially embodying the fact that its existence depends upon revisiting the same states, the neighborhood of the same states, time and time again after a suitable period of time. So these are the states X. They change according to some flow here with some random perturbations or fluctuations denoted by omega here. Now, the reason I've gone to some length in just casting the mathematical basis of the arguments in terms of the flow of dynamical systems is that there's a well-established and very ubiquitous formulation of the behavior of these kinds of systems that inherits from the fact that if I keep revisiting the same states, then I can treat this attracting set of states that I keep revisiting that characterize me or things like me in terms of a probability distribution that you will find me in this state if you sample me at any random time. And I can write down the mathematics of the way that this probability distribution itself evolves. But we've just said it doesn't change with time because we exist over time. So what we can do is we can solve the equation describing the density dynamics. It's called the Fokker-Planck equation. You may know it or you may not as the Schrödinger equation or the master equation. They're effectively all the same things. The solution to that, the particular solution for things that exist over time, is remarkable in the following sense. Using a particular decomposition, the Helmholtz decomposition, it tells me immediately that things that exist will flow in a way that can be described as a gradient flow on the log probability of being in any particular state. I'm going to give you some intuition as to how this equation unpacks, because I think it's quite interesting, but also just to illustrate its simplicity. What we're basically saying is that Well, let's imagine that I placed a drop of oil in some water or on, say, a sheet of blotting paper. Now, the kinds of systems that dissipate that we're not interested in, that don't self-assemble and don't have this attracting set of characteristic states, they would behave a little bit like this, that the ink molecules would diffuse throughout the solvent until they dispersed everywhere, subject to the random molecular fluctuations. The systems that we're talking about, usually living systems, behave very differently. They appear to gather themselves up and assemble in a restricted number of states or places that they could be. In other words, it looks as if their states are flowing up concentration gradients, resisting or offsetting the random fluctuations that will be dispersing them. And that's all that this equation says. It just says that any system that exists can be described in terms of its dynamics, its flow, its movement, its evolution, and that flow can be decomposed into two components. There's the part that gathers things up, that resists the entropic erosion and dispersion, dissipation, decay, dilution, that is this component here, that's proportional to the amplitude of those random fluctuations, gamma. And then there's another component that's at right angles to that, that circulates on the isoprobability contours. It's called solenoidal flow, and this is denoted by the Q here. So anything that exists can be written down in terms of its dynamics, in terms of this decomposition into a gradient flow that flows up the concentration gradients and this circular or solenoidal flow. And you'll all be familiar with this very ubiquitous description of dynamics when you're looking at water flowing down the plug hole. So the gradient flow is going downhill and the circular flow is the swirling around that one witnesses. So that's how things that exist behave dynamically. What about the Markov blanket? Well, what is true of all the states is true of the active and the internal states. So at the same time that the internal states look as if they're performing a gradient flow on the log probability of the blanket states, it is also the case that the active states are doing the same. And I'm going to offer this as a mathematical image of perception changing our internal states and action changing our active states, but in the service of looking as if we're increasing the same quantity, and that quantity is this log probability of the blanket states. So what does that mean? Well, it's probably something that you're very familiar with, depending upon your commitments academically or the way that you understand optimization processes. I've just listed a few things here, and in the hope that you will recognize at least one, if not all of them. The first interpretation of this quantity here, this log of the probability of my blanket states being characteristic of the kind of thing I am, me, or my Markov blanket. We can interpret this as simply an expression of value. These are the states that I aspire to, that I am generally found in. Mathematically, we can approximate this quantity with something known as a free energy or an evidence lower bound in machine learning. But the perspective I'm selling in this interpretation is that all systems that exist will look as if they are performing a gradient flow on this value function. And of course, this is exactly the assumption, the foundation of reinforcement learning, optimal control theory, and in economics, expected utility theory. So that's one perspective. An equivalent complementary perspective is on the negative value. So if you did information theory, this would be known as self-information or surprisal, or more simply surprise, the negative log probability, the improbability of finding my blanket states in this state here, which means that we can construe the self-organization of internal active states in terms of a suppression of surprise. And this leads to things like the Infomax principle, the minimum redundancy principle, and indeed the free energy principle. That's nice because the time average of surprise is mathematically called entropy, which means it looks as if, or it will, any system that exists will look as if it's trying to minimize its entropy. So this clearly is the holy grail of synergetics that tries to understand the imperatives behind self-organization. And if you're a physiologist, it's just homeostasis. It's just gathering your physiological states within bounds to preclude an entropic dispersion and wandering into non-viable or highly surprising physiological states. I'm going to pursue another interpretation, which is more statistical in nature, inferential in nature. In statistics, in particular Bayesian statistics, the probability of the blanket states given a Markov blanket or given me can also be interpreted as something called model evidence or marginal likelihood, Bayesian model evidence. So this is basically saying the states, the internal active states, are changing in a way that appears to be maximizing model evidence. And that finds a nice home when unpacked in terms of the Bayesian brain hypothesis, evidence accumulation, and as we've heard in the introduction, things like predictive coding. So if it's the case that anything that exists should look as if it was doing some sort of prediction or modeling of what's beyond its Markov blanket, then we should be able to simulate that and show its emergence in any self-organizing system that possesses a Markov blanket. So what I'm going to do is briefly show you some simulations of a little universe that we've engineered precisely to show or to ask the question, can we evince this kind of mechanics, this kind of synchronization between the inside and the outside? So what we've done here is just built a little world comprised of 128 macromolecules. The details are not important, the same phenomena emerge irrespective of the differential equations one uses. All we need to know is that they're all loosely coupled, and we can see them bubbling away to, at the bottom of a potential well here. And you may be asking, well, why have I done this? What are we going to do next? Well, because we've written down the equations of motion that underwrite the flow that we've been talking about, we know what influences what. We know which molecules, synthetic molecules, influence which other synthetic molecules, and we can preclude action at a distance. And in virtue of that, we can now define the conditional dependencies that define the Markov blanket. So the hope was that we'll be able to find a little creature living in this synthetic primordial soup, defined purely on the basis of its Markov blankets, the parents, the children, and the parents of the children, defined by this adjacency matrix. And here indeed is a little viral-like particle wiggling around in the middle of this synthetic soup, in little cilium or tail here, where the internal states have been color-coded with blue. The active states that typically in these simple simulations usually underlie the sensory states in magenta here, pushing them into the external states, external milieu in cyan here. So this simulation reveals that there is indeed a little creature living in the middle of this soup that's quite happily attaining and maintaining its visiting its attracting sets, maintaining its technically non-equilibrium steady state. But the question now is, can we find any evidence that the internal states are somehow maximizing the evidence to some implicit model of what's going on the outside? In other words, do internal states appear to infer the causes of their sensory states? Some people in philosophy like to call this self-evidencing, soliciting evidence for your own existence. And it's relatively easy to demonstrate that indeed this process is manifest. This example here is used to illustrate the simulation of synthetic event-related potentials used in cognitive neuroscience and electrophysiology. But just to quickly walk you through it, because what I want to get to is this underlying construct called a synchronization manifold. What we've done here is ask, are there any mixtures of the internal states that will predict the motion of the external states? So this is a little bit like asking, are there any patterns of neuronal activity in the visual brain that accompany motion, visual motion outside, that is registered by our sensory epithelia? And indeed, it is easy to find this. This has to exist, and I'll explain why in a second. Here is an illustration. So what we've done here is take a mixture of motions, fluxes of the external states, shown in cyan, the prediction of those and the 90% confidence intervals based just upon the internal states, remembering that the internal states can't see the external states. All they know is what they, how the external states impress themselves on the sensory states, and the influence of the sensory states by the active states on the internal states. And we can see there's a remarkable correspondence between the implicit knowledge, the inference predicated on the internal fluctuations about what's going on the outside, despite the fact that there is no direct access. And indeed, if we gather together little excursions here and average them, we can simulate event-related potentials. Here's an empirical example from monkey electrophysiology. So you may be asking, well, how does this happen? Why is it the case? Well, it must be the case in the sense that for any given blanket state, there must be an average internal state and an average external state, which means there must exist for any given blanket state the expected internal mode of activity and an external mode of activity. And all we're seeing is fluctuations on this synchronization manifold. And I'm using the word synchronization manifold just to bring to closure the first half of this talk, with a nod to what has been understood for centuries, and in particular the notion of generalized synchronization, or synchronization of chaos, noted by Christian Huygens many, many years ago. And most of you will be familiar with this. It's the observation that suspend two clocks from the same wall or beam, and inevitably, after a period of time, they will start to oscillate in synchrony. They will become entrained, they will become aligned. There is no other solution. And this is basically just an illustration of this fundamental property of coupled dynamical systems. In this instance, we're coupling the inside to the outside vicariously through the blanket states. So here's actually a drawing by Huygens with two clocks suspended from the same beam. So from our point of view, one clock or one pendulum can be the internal states, and the other can be the external states, and they are coupled through the beam in terms of the blanket states comprising the active and the sensory states. So I like this construct because it illustrates the complete symmetry here. So if you subscribe to this interpretation of synchronization, where the inside is trying to, or you are trying to infer what's going on in the world, then you also have to accept that the world is trying to infer what you're about and what you're doing. And that's not an unsensible interpretation when it comes to things like niche construction and the like. However, we are going to try to get back to this notion of synchronization through another route. But let me just first of all summarize what we've done with all the heavy lifting in terms of the physics. What we're saying is that the existence of a particle or a person, anything that exists, implies a partition of a system state, systemic states, into internal, blanket, namely sensory and active, and external states that are hidden behind the Markov blanket. And because active states changed, but are not changed by external states, they're going to reduce the average surprise or the entropy of blanket states. And this means that action will appear to maintain the structural and functional integrity of the blanket. And some people like to discuss this in terms of self-assembly in chemistry, or in the life sciences, autopoiesis. Internal states appear to infer the hidden causes of sensory states by increasing their Bayesian model evidence, namely self-evidencing, and actively influence those causes via what is often called in my world active inference. Just one little twist here for philosophers. There is an argument that the internal states in virtue of the existence of the synchronization manifold, parameterize probabilistic beliefs about external states, and one can unpack that in terms of information geometry and complement a Cartesian dualism with a Markovian monism. But we're not telling that story today. So yes, this is just a little interlude. This is one of my postdocs went to America to work with Mike Levin at Tufts, and a few months after arriving, he and his wife had a little baby, and his wife bought him a Markov blanket. So here is Kira, the little baby, with Franz's Markov blanket. Here is Markov blanket. So if you want a Markov blanket, they are available in America. So we've done the statistics of life. What I promised I would do now is just rehearse exactly the same story, but from the point of view of a neuroscientist trying to understand sentience and how we make sense of the world. So I'm going to unpack this part of the talk in terms of the basics, the fundamentals of the anatomy of inference in terms of predictive coding, with a brief focus on canonical microcircuits and in particular sensory attenuation, because I think that's a particularly important aspect of the physics of sentience, particularly in psychiatry and indeed mental health. And then conclude with an illustration of all this in action. And my fond hope is to get back to synchronization and what it means for models of the world, where the world includes other things like me, and indeed could include me. So the anatomy of inference. All of this is predicated on the underlying notion that can be traced back to the students of Plato, I think best articulated by Helmholtz, as we'll see in a moment. The notion that perception rests upon a constructive act. It's a perspective on perception, which is in contrast to 20th century sort of outside in filtering sensory information. It rests upon an inside out constructive act where you construct predictions or hypotheses that best explain the signals and sensations of your sensory states or your sensory epithelia. So you have to have something in mind as a potential explanation for your sensations before you can perceive it. I think this is beautifully illustrated by this painter famed for doing still life oils that, when viewed from a different perspective, give you a very different percept. So if previously you saw a bowl of fruit and now you see a face, the key thing is you brought that face to the table. That is your explanation. It's this inside out act that now enables you to find a better explanation, a simpler explanation for why you're perceiving or sensing this particular pattern of sensory signals. So Helmholtz would, I think, in the life sciences and the physical sciences, be the person who first articulated this most clearly, nicely illustrated by this sentence or quote here. Objects are always imagined as being present in the field of vision as would have to be there in order to produce the same impression on the nervous mechanism. So again, speaking to the notion that it is the impressions that you get on the sensory epithelia are explained by what would happen if this was the cause, and the cause has to be imagined in a mindful way. And clearly this is very much akin to Richard Gregory and other seminal psychologists of the 20th century who formulated perception as hypothesis testing. Again, this notion that using sensory evidence, sensations, sensory states, as evidence for or against a perceptual explanation or hypothesis. And if confirmed, then you commit to that, and that is what you see, as opposed to what you are looking at. These ideas have been used to great effect in a technical arena. It's particularly machine learning by people like Geoffrey Hinton, and in a slightly more translational setting by people like Peter Dayan. And indeed, they came up with the notion of a Helmholtz machine as a machine learning or neural network formulation of this basic idea, borrowing ideas from Thomas Bayes and in particular Richard Feynman's free energy or variational solution to the problem of this difficult inference problem that we all face when finding the best explanations for our sensorium. Let's just go back to Helmholtz. Producing impressions on the nervous system. So this fits very nicely with this Markovian blanket construct. So what we're talking about here is, if it is the case that to be is to perform gradient flows on evidence, model evidence, what I am effectively saying is that I will appear to try and explain the best explanation or causes for the sensory impressions or the shadows of my sensory states, my sensory veil. So I will be trying to discern or represent what is causing these sensory shadows here. And using the maths that I presented in the first half, one can sketch out how our brains actually do this in a relatively straightforward way. So these equations, again, may look complicated, but once you get used to them, they are remarkably simple, and yet may explain how our brains and our neuronal message passing actually implement this fantastic act of being able to explain what's causing our sensorium, to produce those fantasies that are veridically endorsed by the sensory, our sensory evidence that we gather with our eyes and our ears and all other organs. So let's just come back to this gradient flow and focus on the internal states. So here's our gradient flow on this log probability. Under some simplifying assumptions, Gaussian assumptions, we can write this expression in this form here, which is a mixture of two things. The rate of change of my internal state, so my neuronal activity, can be broken into the solenoidal part, which is in engineering known as a prediction. So it's a prediction of what I would, the states of the world in the future without observing any new information. So nothing is actually changing in terms of the underlying surprise, because it's a prediction about things I haven't yet seen. And then a prediction error, epsilon, which is the difference between what I predicted and what I actually observe. And this gradient flow basically is just saying we're going to minimize the sum squared error, weighted by their precision pi here. So just to try and give you an intuition of what that sort of, how that would work in a sort of coarse-grained fashion. Let's imagine that we have this sensory impression here, this shadow on our sensory epithelia, and we had some expectation or mean explanation mu here, that the best explanation was of a howling dog. And if I had a generative model G that could generate from this expectation what I would have seen, my sensory states that would have been produced if this was right, then I can compare the prediction generated by the generative model with the actual sensations and elaborate a prediction error. And then I can simply use my prediction error to optimize or change my expectations until the prediction error has been minimized, and at which point I will have a perfectly good explanation for my sensory impressions. And that changing, that Bayesian belief updating, that evidence accumulation is just this gradient flow. It's just minimizing prediction error. Notice that the name of the game here is to minimize prediction error, or to maximize the probability of the sensory or the blanket states under a particular model of the world that is generating the predictions. We'll never actually know what caused these sensations, but that's not the point. If I can get through my life minimizing prediction error, job done. And of course, that job is done by this gradient flow up here. So this provides a nice and parsimonious, very simple picture of active sentience. So we can forget about all the Fokker-Planck equations and the gradient flows And we can say that we can explain everything in terms of minimizing prediction error, which means that we can understand perception as the changing of internal, for example, brain states to supply predictions that are as close as possible to the sensations. And that would be a canonical way of minimizing prediction error. And we can regard that as perception, changing predictions. However, there is another way of minimizing prediction error. We could actually go and resample our sensory states, our sensations, to make them more like the predictions. And this involves actively soliciting new sensations from the environment by looking over there or by touching this or touching that. And that gives a nice explanation for changing sensations to minimize prediction error. So both action and perception are simply there in the service of minimizing prediction error. So what would that look like in a little brain? And I've deliberately chosen a bird brain here because I want to use bird song as a little simulation at the end, just to illustrate and make concrete some of the phenomena that we've been talking about. So imagine this is a piece of neuroanatomy from a bird brain. This is the auditory thalamus of a songbird. It receives some sensations. So let's assume that the bird is currently listening for something. It receives these fluctuating sonogram representations of sensory input, time, frequency. And in the absence of any top-down predictions, there is the sensations just become the prediction error. They go up to the higher vocal center, for example, where they drive through this gradient flow expectations that try to provide predictions of what's coming in until such point as the predictions match the input and the prediction error is quenched or resolved. However, at the same time, while these first order predictions are fluctuating, being driven by the ascending prediction errors, they are also in receipt of top-down predictions from a higher area, say area X in the songbird's brain. And the same mechanics ensues, that there's a difference between the activity here and the top-down prediction that elaborates a prediction error that's sent forward to give better top-down predictions of the first order predictions that generate and try to suppress the first order prediction errors. And you can see how you can build this hierarchically into a deep generative model of the sort necessary for inferring what's going to happen next at different temporal scales, a narrative, or in this instance, bird song. This is a useful explanation for listening, but notice that we've also included in the things, the sensations that have to be predicted, the sensations that are reporting the status of my motor plant, in this instance, the voice box of the bird here. So if I were able to, if I was listening, then I would not be predicting any sensations from my articulatory muscles, any stretch receptor signals. However, I can use exactly the same generative model, the same machinery, predictive machinery, to actually reproduce and sing. And all I need to do is basically switch on by increasing the precision of the descending predictions of what I would feel if I was actually producing this sensory input. And then I would have a difference between my top-down predictions and what I'm actually sensing from my muscles, and I would have a prediction error, and I could use that prediction error to drive my expectations, and in fact I wasn't singing. Or I can send them back outside to the world and actually cause the muscles to move until they supply the predicted signals. So all I've done here is sketch a computational anatomy that is isomorphic, exactly the same as a classical reflex arc, where the way that we move, and indeed the way that we secrete in terms of autonomic action, rests upon top-down predictions, providing a set point for classical reflex arcs that these peripheral prediction errors actually drive and fulfill. And all this requires is a sort of yin-yang, or a selective gating of whether I am attending to switching on the precision of the prediction errors pertaining to proprioception, to action, or exteroception, in this instance, auditory sensations. So this illustrates a very important role of precision in contextualizing whether I'm passively listening and not moving, or whether I'm actually generating the sensations actively and implicitly also attenuating the consequences of my own action, sometimes referred to as sensory attenuation. Technically, the story that we've just told, this sort of predictive coding with reflexes formulation of active inference, is a story about the top-down predictions, descending predictions, playing the role of corollary discharge, predicting stuff that I'm sensing in the exteroceptive domain, and at the same time bilaterally generating predictions of proprioception that are interpreted as motor commands by the peripheral nervous system and my neuromuscular junctions. From the point of view of the control of precision, this mechanism sort of switching between sensory attenuation and sensory attention or selection, sometimes interpreted in terms of attention being, if you like, the psychological homologue of this sort of precision engineered message passing here. I just want to drill down on that because I'm going to use that in the final couple of slides to simulate dyadic interactions. So just to show you how potent this precision modulation of the prediction errors that we're trying to that we use to select the kinds of prediction errors that we want to minimize or that we believe convey precise information for our belief updating. I'm going to play a little game, if you'll allow me to play this game. It's illustrative of one of the clearest examples of sensory attenuation, which is called saccadic suppression, but I'll explain how and why just after illustrating its potency. So this is not going to work very well given that you're all very remote, but could you, if you are a man, do one task, and if you're a woman, do another task? And the task is as follows. In a moment, Sherlock Holmes is going to jump from this side of the screen to the other side of the screen. And your job is to tell me whether any aspect of this picture of Sherlock Holmes changed when it goes from here to here. I'd like the women to focus on this fixation point here in the center. So they have to keep their eyes still and tell me whether Sherlock Holmes changed en passant whilst fixating on the cross. Conversely, the men, I'd like you to focus on Sherlock Holmes and try and track Sherlock Holmes. And what I want to know is who's the best at being able to detect whether or not anything changed in the picture of Sherlock Holmes. So if you can all do that, I'm going to pick on Lydia as representative of women to give me her answer, and Tim as representative of men to give me the men's answer. So Lydia and Tim, can you focus, if you're still there, on this particular little task? Right. So 3, 2, 1, and then he's going to jump. 3, 2, 1. Lydia, can you hear me?
Hi. Yes, I can.
What did you think Sherlock Holmes changed in any aspect?
Well, I saw something flash up in the middle.
Oh,
what
did you see?
I think it said, "Did you miss me?"
Okay, that's Tim. Tim, are you there?
I'm there. I'm here. Yes. I'm
No.
afraid I didn't see anything. I didn't. No.
You didn't see anything at all. No change in Sherlock Holmes. But Lydia,
a good detective.
so beautiful. That is a lovely illustration of the power of saccadic suppression or sensory attenuation in the oculomotor context. So what Lydia, well done. That was, you only had about 50 milliseconds to see that, but you did indeed see Did You Miss Me? And the idea here is the reason that you, Lydia, saw this was that you were not suppressing the precision of your visual prediction errors because you weren't moving. Tim, on the other hand, had to suppress the visual prediction errors because they were a consequence of its active sensing or visual palpation of the world. So this is a lovely example of enforced sensory attenuation, where we're basically transiently blind or transiently suspend our attention when we cause the sensations. And of course, when we move our eyes, there is an enormous visual flow or optic flow induced simply by our eye movements, which we cannot see. And in virtue of the fact that Tim could not see it whilst he was moving his eyes, he couldn't see anything else either, which is why you, Lydia, were the only person that could actually see the did you miss me? So I think this is a wonderful example of, hardwired sensory attenuation that really has a profound influence on how the sensorium updates our belief and how that depends exquisitely on agency and action. And what I want to do now is just to close by leveraging sensory attenuation and augmentation that underwrites whether I'm listening or talking, or whether I'm listening or singing, to simulate now dyadic interactions. So previously we've been talking and simulating little creatures exchanging with the external world. What I'm doing now is making a further move and putting two Markov blankets face to face, as it were. So the internal states of one blanket are the external states of another blanket, in the hope of simulating dyadic interactions. But to do that, to preserve the conditional dependencies, I have to do turn taking. And I'm going to use this precision mechanism to turn take. So one, in this instance, it's going to be a bird, is listening, and then it's singing. And then it's listening, and then it's singing, and vice versa for the other bird. So when we integrate those equations, I'll just let the birds sing. When we integrate those equations of motion, that predictive coding equation with the prediction and the gradient, the prediction error minimization part of a neurobiologically plausible sort for the generative model that I've just described for singing and listening, we can simulate what would happen if two birds were singing in the same locale. But what I've done here is separate the two birds so that they can't hear each other. So what you're listening to now is what one bird is actually hearing. It can't hear itself. Sorry, it can hear itself, but it can't hear the other bird. And then now simply going to repeat the simulation, but bringing the two birds within hearing range of each other. So now they can hear each other. And then I'm going to track the internal states at different levels in this synthetic cortical hierarchy that are providing the predictions and the prediction errors for the song that you've just heard. And now, if we listen to what is perceived by the first bird, you can now hear a continuous melody. And this melody is composed of itself singing and then hearing the other bird, then itself and the other bird. And in contrast to the previous slide, what we're seeing here is a synchronization. And this synchronization ensues because both birds have the same generative model. They both have the same beliefs about what's out there. And in this instance, what's out there is exactly the same as itself, which means that this is a really powerful way to minimize surprise or prediction error, in the sense that if you are like me and we are in exchange, then you become very predictable from my point of view, because anything that I do, you are doing, and vice versa. And this holds for you as well. So dyadically, altogether, we can now minimize our free energy or minimize our prediction error, simply because we are committing to the same narrative, to the same sensory states and active states that generate the sensorium, and our sensorium is shared, and it's mutually predictable simply because I can assume that you are like me. And under that assumption, and when two things are sufficiently similar and they can learn mutually to be sufficiently similar, then we see the emergence again of the synchronization manifold. So here, in a different context, but it's mathematically exactly the same construct that we looked at with the simulations of the primordial soup. What I've done is tracked out the new brain activity, if you like, the neural activity generating predictions when the two birds couldn't hear each other at the different levels in this synthetic cortical hierarchy, and then exactly the same neuronal activity patterns when they can hear each other, just to show you how they align, how they become synchronized. Of course, we now know that it couldn't be in any other way, in the sense that this is the kind of coupling that is the non-equilibrium steady state, or it is this attracting set of states that must emerge very much like Huygens clocks. So that's an illustration of synchronization in terms of communication. In this instance, a very elemental communication, literally singing from the same hymn sheet in order to be able to infer a very elemental, if you like, theory of mind. The last slide is really an invitation to think about what that means for the way that we learn our generative models of the world. To exploit this free energy minima, this prediction error solution in a world that is populated, constitutes creatures like me, I can assume that every creature like me is like me, and we're all singing from the same hymn sheet. But to get there, I have to learn that the world out there comprises creatures like me. So here is the challenge for a newborn. First of all, the newborn has to distinguish between the things that it can act upon and the things that it has no control over, in order to develop a generative model that enables it to recognize those reflexes and parts of the world that can be controlled and can't be controlled. But the even greater challenge then is to recognize and to learn via this surprise minimizing, free energy minimizing prediction error mechanism applied to the connections and the structure and the parameters of the generative model, to learn that the best explanation for its sensorium is the fact that many of the sensations are supplied by something else, another, and in particular a mother that is something like me, which will be the final stage, a very elemental simplistic sense of learning that there are things like me out there. So having developed a sense of mother, then one might suppose that that a neonate might test then the hypothesis, well, perhaps I am like mother, and thereby leading to a sense of self. So in a rather cursory way, I've managed to get to the what was promised in the introduction from Peter about agency and a sense of self, but in a way really which is more an invitation to interpret and discuss whether the underlying physics of sentience really makes sense in terms of speaking to these fundamental questions about selfhood and relationships with others. I'll end with a quote from Feynman. It's usually a technical quote, but I thought this would be more appropriate in the current context. The highest forms of understanding we can achieve are laughter and human compassion. And with that, it just remains for me to thank all the people whose ideas I've been talking about, and most importantly, thank you for your attention. Thank you very much indeed. And I'm going to pass now back to Peter.
Thank you. Thank you so much, Karl. I've been monitoring some of the comments in between, and if I can just cite to you a few: enlightening lecture. Thank you. This is so interesting and brilliantly explained. I've got some questions, but just to say, in kind of try and do a little bit of translation. What is remarkable about your view is really that it's like the picture that you showed. You've turned perception upside down in the kind of active inference framework. That there is that the traditional notion of perception and action and everything between is not a kind of the end point of a whole long line of processing, but really something that we generate from inside and then compare with out there. Now, those of us here working clinically, and a number of questions from that perspective, have known this all along. We have been, you're not telling us anything new. We've known this, that people just interpret their world and they try and minimize prediction error, and they change the world until the prediction error is minimized. And some of that has very painful consequences. Some of it has distressing consequences in psychopathology. And one of the questions, and there'll be more technical questions, but one of the questions that people really want you to address just a little bit, because I know that you have done, is how would you, brilliant though your model is, how would you see mental disorder? How would you see psychopathologies in terms of prediction error? And is there a risk, which I don't think there is, but I think we could do with the reassurance that is there a risk that some sort of innate disruption in minimizing prediction errors could be at the root of mental disorder, or is that a consequence of historical experience, into consequence of personal experience? Over to you, Karl.
Oh, excellent question. So just speaking to this sort of, turning things on their head, it is, I think, a nice example of what Dan Dennett calls a strange inversion, but clearly not strange to you, and people actually work with people. But for some people in machine learning and artificial intelligence, it's certainly a strange inversion, but much more natural for people who work with actually also real artifacts of an artificial sort in robotics. But the deeper, I think, more challenging question, which I'm sure we'll drill down to, is where does this mechanics yield some interesting hypotheses about false inference and the concomitant behaviors that attend, or belief states that attend false inference that we see in psychopathology of its various flavors. And I think you've carved up the answer into two domains already, which is part of it is false inference in the moment. What leads? What's the first principal account of a false belief, or indeed a false percept, and in the moment? And then there's the other questions, which are more about the learning of the generative models. So there's the deployment of a generative model, inverting it in the moment, given the sensory evidence, given all the evidence from your interception, from your pro-social interactions at hand, to use your generative model to infer what's going on at the moment, and how I can sample or create new information to make my predictions come true, as opposed to in a developmental, or indeed actually in any experience-dependent setting, the updating of the parameters, the contingencies, the lawful aspects, the structure of that generative model that would underwrite the emergence of a sense of agency, attachment, possibly a description of the development of a dyadic relationship over days, months, weeks, and years. So in the first domain, there's a really practical answer, and it just comes from the empiricism that one can find in academic psychiatry and academic neurology. When one looks at the process theories and neuronal process theories that mediate this gradient flow, then it seems that both the nature of false inference, the psychopathology, if you like, and the neurophysiology almost universally identifies a failure of that precision. So it's a failure of that sensory attenuation that we were illustrating with the saccadic suppression, but at a much higher level. So whether you're talking about Parkinson's disease, failure to attenuate proprioceptive information that I'm not moving, and therefore never being able to develop the fantasy that I'm moving, leading to psychomotor poverty, or whether it's the hallucinosis of organic psychosyndromes, or indeed schizophrenia, where you, or perhaps the poster child here would be autism, where you are unable to modulate or attenuate the precision afforded sensory evidence, so you become glued to the sensorium. You fail to develop deep, centrally coherent generative models of your world. You cannot disattend. Nothing is surprising because nothing, everything is worthwhile predicting. So you can't have illusions, you can't have mismatched negativities, or ball responses, all cardinal signs of, of things like schizophrenia. So you put that failure of sensory attenuation in a developmental context and just ask what it must be like to be born into a world that you're trying to make sense of, and all your sensing is possibly a rattle or suckling or nurturing behavior or filative touch from your mother. And you're trying to make sense of the world, but you can't disattend from anything to actually drill down and start to build a deep model that provides a parsimonious explanation of the kind, mother is a creature. She is an object out there that's doing stuff to me. I cause this bit and she caused that bit. So, then the game gets exquisitely difficult in terms of understanding the profound implications of a failure to suspend your attention in an apt way to realize your agency or disambiguate, I caused that or you caused that.
Mm-hmm. I mean, there is a finding that originally John Watson brought forward to the developmental world, that babies up to the age of about 3 months attend with preference things that are perfectly contingent with their actions. After 3 months, they prefer to attend to things that are clearly not perfectly contingent, nearly contingent, but not perfectly contingent. And that autistic children do not have this switch, the 3-month switch. Would this be consistent with what you're suggesting?
Yes, it would. I didn't know that. That's fascinating. I mean, if I had to build a baby in silico, that's exactly what one would hope would happen in the normal development. You've got to learn what bits of this world, can I act upon, and what bits can't. That's the first thing that you need to, the self-discovery without any sense of selfhood per se. But then you get to the more interesting bits. Well, I thought I could control this, but perhaps there's another agents out there, and then you start to, find that much more epistemically attractive. It has much more epistemic affordance. These things I thought I could control, but in fact, someone else might be out there. Yeah, marvelous.
Let me try and squeeze another question. So, enlightening lecture, thank you. I'm a psychologist working with parents who struggle to relate to their kids, who engage in very high-risk behaviors. Part of the issue is that often parents overreact emotionally, feeding into the behavior. Staying calm and acting counterintuitively is a challenge. So thinking about the Markov blanket model, where would you start with these parents? Not an easy question.
It's not, because I was immediately trying to answer it as a psychiatrist, and
forget that. You're a physicist.
As a mathematician. As a mathematician, all that this very simple-minded treatment of dyadic interactions brings to the table is the the notion of generalized synchrony, synchronization between you and your loved ones, or you and your clients, or you and your patients, which would basically says that to have a harmonious, aligned interaction, you have to be in a like mind and singing from the same hymn sheet. So if you are, and all, that hymn sheet covers all modalities, from interoception, from verbal, non-verbal cues, but the synchronization, the alignment is still in play, even to the level you can measure it in terms of your body movements, blushing, for example, pupillary dilatation, all of these subliminal cues that tell you about the state of your embodied brain are mutually available. And the trick would be, I would imagine, to try and synchronize them. So just on that mathematical basis, you have to put yourself in the same state of mind as the child, in the fond hope that the child will reciprocate by putting themselves in the same state of mind as you. One little trick here is that the rate at which two coupled systems converge to their common ground depends upon the precision or the confidence in the predictions of the two. So if there's an asymmetry there, you can often get a teacher or a parent or a therapist who has more, if you like, precise beliefs higher in the model, that will move towards the less precise Markov blanket or client or child, but will move less quickly than the child moves to the parent. And clearly, you see that in a natural setting, just in terms of schooling. It is generally the case that the teacher is older than the child, and the teacher is more confident about what the child knows. But at some point, there is a meeting in the middle, but it's not always in the middle. So that was a really stupid answer, but at least it was faithful to the mathematics.
One final question to test that breadth that I was boasting on your behalf. And here is, I'm sorry, could a problem in the stability or structuring in the Markov blanket be thought of as a failure or weakness of psychic defense? And would the introduction of entropy or dissolution point to links with Freud's ideas of the death instinct?
Yes, I mean, there are all sorts of really interesting ways you could take that question in terms of structure learning, but let me focus on the Freudian interpretation or homologues here. I think if there is part of the audience that likes this, to understand the parallels and the homologies and isomorphisms between your Freudian take on free energy and the more mathematical Richard Feynman take on it, then Mark Soames is your man. He's written beautifully about this, and would normally start the story by noting that Freudian formulations inherited quite a lot from Helmholtz. So had Freud known Feynman and had tried to develop Helmholtzian ideas, it's more than likely his free energy would be the same as that used by people like Geoffrey Hinton and Richard Feynman. And interestingly, when Mark Soames goes into this in great detail, he actually converges on the same thing that we were talking about before, which is this precision. That I'm not sure that we can, we don't have time to get to ego dissolution and the like, but one important autopoetic aspect that maintains the integrity of the Markov blanket is exactly this attending and disattending. It's selective and appropriate switching on and off of how the sensory states get in and influence the internal states, and then vicariously your actions upon the world. If that breaks, everything falls to pieces. And that certainly is Mark Soames's story, based upon sort of a theoretical neuropsychology based upon the importance of ascending modulatory neurotransmission systems for example, dopamine and the like, but not just dopamine, all these classical neuromodulators, because if it's the physiological mediation of this precision control is via selection and postsynaptic gain, which is neuromodulation. So it's not surprising that a lot of the neurochemistry and the pharmacology of psychopathology fixes upon these neuromodulators, and furthermore, this is exactly Mark Soames' conclusion in terms of the failure to resolve free energy lives at the seat of the soul is essentially the source of origin of the ascending modulating neurotransmitter systems that are exactly there to provide this gating, attenuation, selection behavior that preserves the Markov blanket in the sense that we've been discussing.
Karl, this is an absolutely brilliant lecture. You are everything that I have advertised you to be. It is obviously a revelation, but a revelation in the direction of helping us understand sociality, helping us understand how ultimately the brain and our capacity to create a world that's consistent with our hypothesis actually folds into a continuum that we are living every day but as you said, in a very strange, as a very strange function of time, as a very strange function of time. And it's to have a mind like yours that actually can bridge the abstruse writings of psychoanalysts with the cutting-edge writings of physicists and neuroscientists in between, and whilst maintaining an identity as somebody who's concerned with mental health. You're a remarkable human being. You really are. And we are enormously privileged to have had you here this evening and to be able to benefit from your wisdom. So thank you so much for joining us. Thank you.
Thank you. Thank you so much.